Good morning, everyone. A warm welcome to uRos2020 from freezing Vienna. This is the 8th edition of this conference, but the first time as a virtual event. We had big plans for the event in Vienna, an R crash course, Unconf uRos, a hackathon, 4 tutorials, 63 live presentations, 3 keynotes. We even already ordered 150 air mattresses. 2 of them are in the background of my picture. In the past, we had about 100 participants. For Vienna, we planned with about 120 participants. So maybe this virtual event is a chance to even increase the number of participants we have to this event. For the virtual event, we had to streamline the program to make it fitting for this new format. So we kept 2 exciting keynote speakers, Isabel Molina, who will speak directly after me today, and Matthias Temple with functional data analysis, spaces with an application to spatial temporal population data tomorrow morning. It is not morning everywhere our presenters come from. They come not just from all over Europe, but also from more distant locations. For example, from Argentina, Morocco, Colombia, Mexico, Indonesia, or Japan. There will be 5 sessions with live presentations, and we have a session with 8 exciting pre-recorded presentations. These pre-recorded presentations are already online on YouTube. The link to it is provided on our webpage. Take a look, they are really worth seeing. If you want to engage with the authors, you just post a question or a comment right in the YouTube comment section. Please be aware that we will record this whole online event. Speakers already know about this and consented to it. So good news is we will publish all the presentations also on our YouTube channel soon after the conference ended. Beside the WebEx event, some of you are watching right now. There's also a live stream via YouTube and Facebook. So how will questions work? This works directly within this WebEx event tool. There's a question and answer section, and everybody can ask questions there. If you do not see it right now, there should be a menu in the bottom right corner, at least that's where it is in the desktop version of WebEx, where you can make it visible. Some of them then will be answered live by the presenters as they are selected by the session chairs. As there might be more questions than time allows to be answered live, the presenters can answer the questions also directly within the Q&A facility of WebEx in writing. Yeah, before moving on to the actual content of the conference, I would like to thank a few people. First of all, the management and my colleagues of Statistics Austria, who supported me in the idea of having the conference in Vienna, even if this did not happen at the end, or in the end. A big thanks also to the members of the scientific committee who read and reviewed all the received abstracts. Thank you also to Nicoletta, Ciprian, Anna, Bogdan, and Mark from the organizing committee for working together with me on the program, the homepage, and many other things. And of course, also thank you to all speakers for this conference and the persons who supplied the pre-recorded presentations. So enough with the welcoming. It's soon 10 o'clock, and we are excited to actually start the conference. We're happy to start the conference with a keynote given by Isabel Molina with the title Small Area Estimation Using R with Application to Poverty Mapping. She is Associate Professor at the Department of Statistics at Universidad Carlos III in Madrid since 2009 and has published more than 30 papers in peer-reviewed statistical journals, most of them on small area estimation. She has received several awards. Currently, she is Associate Editor for scientific journals like survey methodology and the Journal of Survey Statistics and Methodology. She is co-author, together with Professor Rao, of the Wiley book Small Area Estimation, and also co-author of the air package SAE for Small Area Estimation. I'm really looking forward to her presentation. So please, Isabel, the floor is yours. Start your presentation and share your screen. Thank you.
Okay. Thank you very much, Alexander, for the introduction. And also, I would like to thank all the organizers of this conference. So it is a great pleasure for me to present here in a conference that is devoted to the promotion of R in official statistics. I always say that when you start using R, then you don't want to use any other software anymore. So it's a really honor for me to present here. So I'm going to share my screen now. I cannot share. I'm not allowed to share.
Yeah, I think it takes just a second. Does it work now?
Yeah. Okay. I also wanted to say that it's a pity that I cannot see all the audience in person. I would have liked to, and so in any case, I am here, and everyone who wants to discuss with me, I am available. But in here after the talk, or also in other way, okay, with my email or whatever. Okay, so my presentation is about small area estimation using R with application to poverty mapping. But the truth is that I decided to include the two, I would say, most successful applications that I have done to official statistics. And they are not both about poverty mapping. So one is about labor force using Swiss data, and the second one is on poverty mapping in Palestine. Okay, so I will start doing a brief introduction to small area estimation for those who are not already introduced in that topic. Then I will describe these two applications to the labor force using Swiss data. And I need to thank the Swiss Federal Statistical Office because it was a joint project with them, a very fruitful project for several years, and with really good results that you will see later, at least some of them only. And yes, I need to thank them for their support. They made the data available and prepared it in a great way, and also their comments were always really helpful. And also in the second application, it was in a project together with the UN ESCWA, which is the United Nations Economic and Social Commission for the Western Asia. And also the data was provided by the Palestinian Central Bureau of Statistics. And they also did a great job preparing the data and yeah, with their comments. So I need to help all of them a lot. I need to thank them, sorry. Okay, so let me just introduce a little bit the notation I will be using and the basic concepts in a small area. So we work under finite populations. So you will denote the population of size cap n, and this population is divided into subpopulations, which we'll call areas or domains indistinctly, okay? And there will be cap D areas or domains of sizes N1 and cap D, and they form a partition of U. Then from the total population, we have a sample S, okay, of size small n, and this sample, which is drawn from the whole population, has a subsample from each area, okay? That's the subsample of size small nd, okay? So there is a subsample from each of the areas or domains. And I'll denote by RD the sample complement in area or domain D, okay? Then I'll use two subscripts, okay? So D is the area index, okay? And I is the unit index within the area, okay? So YDI will be the value of the variable of interest for the ith unit within the ith area. And the target indicators, the indicators of interest, it is what we want to estimate. They are just functions, general functions of these variables for all the units in the area, okay? Particular indicators of interest that are very common are the area means, okay? Area means. And what is a direct estimator? We call direct estimator to an estimator that is based only on the survey data from the area, okay? From the target area. So the problem is that the sample is drawn from the whole population. The total sample size is large, is typically very large, but when you want to estimate in a subpopulation, the sample size in the subpopulation can be very small. It could be even 0. So a direct estimator is the one that is calculated only with the data from that area. And the typical direct estimators are just for the domain mean. You could use the sample mean, or you could use the Hurwitz-Thompson estimator, which would be using the design weights, which are the reciprocals of the inclusion probabilities, or when the weights are already calibrated, okay, then you would get what we call a calibration estimator, okay? Calibration estimator, and a particular case of calibration estimator is the well-known generalized regression estimator, okay? So those are examples of direct estimators because they use only the data from the target area. So when do we say that an area is small? Okay, so somehow the terminology is not very much correct because it does not mean that the population size of the area is small or that the surface of the area is small. It's not related with that. It is related with the sample size. So it's an area for which the sample size is not large enough, and so the direct estimator of the target indicator has not acceptable sampling error. So in fact, there is no even universal sample size below which we consider an area as small, because it is related, it is linked to the target indicator that we want to estimate. It is not the same to estimate a proportion than to estimate the mean of a continuous variable. For a proportion, you would need a larger sample size, okay? So, and also it depends on the estimator, on the particular estimator that you are using. So we, how to say, established definition of a small area is when the direct estimator that we are considering for the target indicator has sampling error that is not acceptable. And what does it mean not acceptable? Again, there's no, how to say, mathematical definition. Typically, there are some, how to say, levels of relative error. Typically, you measure it in relative terms. So you consider the coefficient of variation. And when it is exceeding certain limits, let's say 20%, 20% is a limit that is considered in several statistical offices as the limit for publishing a statistic. Okay, so every organization establishes its own limits for the relative error of the estimates to be published or not. So when the sampling error exceeds that given limit, then you consider the area as small. So that's the definition that is, I would say, more accepted. And then, so that's the problem. So you don't have enough observations in the area to produce reliable estimates, reliable direct estimates that use only the data from the area. So you have to appeal to what we call indirect estimators, okay? So those indirect estimators are based on borrowing strength, okay? So the idea is to borrow strength from the other areas. How? By making some assumptions that link all the areas, some homogeneity assumptions that link all the areas, typically through common parameters, okay? And this, you can do it making use of auxiliary information. A subset of indirect estimators are the model-based estimators, the set of model-based estimators. So these estimators, the assumptions are formulated in terms of a regression model. Okay? A regression model that relates the variable of interest with available covariates, okay? And this relationship is similar, not the same, but it's similar for all the areas, okay? Typically, I'm saying similar because you should account for between area heterogeneity by including in the model random area effects. So we include in the model random area effects that account for the unexplained area heterogeneity. So not all the areas are, behaving exactly in the same way, but you allow for some variation between the areas. So it's like we don't have, so imagine that our target variable is, let's say, income. So you establish a model between income and factors that affect income, let's say education level, let's say perhaps gender, to be employed or not employed. Okay, so the relationship between the variables, between the income and those variables, okay, is not exactly the same for all the areas, but there is some variation, okay? Unless you would have all the factors that determine income. But in the general case, you typically don't have all the factors that affect income, okay? So you don't have everything that explains income and that explains the differences between income in the different areas. So you have to account for that fact. Okay, there are two broad sets of models, okay? One is area level, the set of area level models, okay? Where the model is established for the area aggregates. So in fact, the response variable in the area level models are the direct estimators, okay? Direct estimators play the role of the response variable in the model, and then you consider area aggregates of the covariates as explanatory variables in the model. And then in unit level models, the model is assumed for the units, okay? So you relate the, let's say, the income of an individual with covariates that are also at the unit level, okay? There is an R package that I developed together with my colleague, Yolanda Maruenda, on small area estimation, and it contains functions for small area estimation and also mean square error estimation, and it includes the basic area level model, which was proposed by Bob Fay and Heriot, and so we call it FH model. Okay, so you have the usual estimator under the Fay-Heriot model and the mean square error estimator by an analytical formula developed by Prasad and Rao. It's a very famous formula. There is also a more sophisticated area level model with spatial correlation, another with spatio-temporal correlation between the areas. Okay, so the areas are observed also in several years, for example, several instants. And then you have the basic unit level model also, which was proposed by Baptiste, Harter, and Fuller, and so I call it PHF model. And also we have the usual estimator and mean square error by parametric bootstrap. So all those are, this basic unit level model is used for estimation of means, of area means. But now when you want to estimate more general nonlinear indicators, then you have to apply another method that is called EV method that I'm going to describe in a while. And so there is a function for that. And you can estimate general indicators that you define yourself as a function, okay? And also you can estimate the mean square error. And then we did include basic direct estimators, the Horvitz-Thompson estimator, and basic indirect estimators. But I must say that for direct estimators, which are typically based on the sampling design, there are other packages that are much better than my function direct. Okay, there are two well-known packages on survey sampling, which is the survey package and the sampling package. But my function is for the case when you don't have any information about the design, but just the survey weights. Okay, only that. And then as indirect estimators, you have available there the post-stratified synthetic estimator and a composite estimator that is called sample size dependent, which is very famous as well, but simple, very simple estimators. Okay, there are also data sets. We have these 4 data sets and some others that are supporting this. And the first 2, in fact, are somehow historical data sets for small area estimation. The milk data set was used typically to estimate Heriot models. And the corn soybean data set was used to estimate, was used in the original paper of Baptiste, Harter, and Fuller. Okay, the original paper that used for the first time the basic unit level model for small area estimation. Okay, and then there are other data sets. There are many other R packages for small area estimation. Surely I'm missing some. Perhaps I don't know all of them, but these are the ones I know. There are 2 pages, don't worry. So there is this YoSci by Johannes Breidenbach, who is a forest researcher in Norway. And he included unit level and area level models. And he included heteroscedasticity that I did not include in my package. Then there is the HBSci from Harm-Jan Boostra, who is in the Netherlands. And he included hierarchical-based methods for the basic area level and unit level models, and also REML fitting, not only Bayesian fitting. Then there is another package for Bayesian estimation, Bayesian methods, and it includes unmatched models, which is very interesting. Sometimes they are needed, and spatial models. And then there is another for counts, which is interesting too, because I did not include any function for counts, specific for counts. Sometimes you can use like the Fay-Herriot model and all the other models sometimes under certain conditions. Then there are two packages for robust methods. Okay, one from Tobias Shaw and another from Sebastian Warholm. And there is one for simulation of data from Sebastian Warholm and Timo Schmidt. There is another on a temporal area level model by the people in Spain. Another from those and another co-author, Esther López Vizcaín, on multinomial area level models. Another on measurement error, okay, same me. And this last one, AMDI, which is a recent package for that it contains many functions for estimating and other tasks for poverty mapping. It's more focused on poverty mapping. So let me now describe the basic unit level model, because it's the model that I will be using in the two applications that I will describe. So this basic unit level model is also called the nested error model, and it was proposed by Baptiste Harter and Fuller, BHF, to estimate crops under corn and soybean using as covariates data coming from satellite images. This is also an important, field of application of small area estimation, okay, to agriculture or to forestry, and they typically consider satellite or other type of images. There are laser images, LiDAR, and they consider the pixels as the population units. So that's interesting. And that is a case, in fact, in which you have covariates observed at the unit level for all the population units, because the population is the image. Okay. So in this model, you relate the variable of interest YDI at the unit level for ith unit in the ith area to the covariates, the available covariates for that unit, okay, through common data, okay? It's common for all the areas, okay? So that is what helps to borrow strength, see? So it's like you are reducing the number of parameters, okay, to P. And P is typically much smaller than the number of areas. To P is the number of covariates, okay? And then you include area effects. And you need to include them because they account for the unexplained heterogeneity between the areas. Okay, that's what I was saying previously. And then the unit error. Okay, and these are the usual assumptions. Okay, for the area effects and the unit errors. Okay, so that's the basic unit level model that is used for a small area estimation. Now, how can we estimate now, let's say, the means in the areas? So when you have a linear parameter, linear function of the variables in the area, okay, linear on this vector, YD, which is the set of variables in the area, typically the estimator that is calculated is also a linear function of the survey data, okay, linear function of the survey data on Y that is unbiased and that has minimum mean square error for the given area D, okay? And that's what is called the BLAP, best in the sense of minimum mean square error, linear function on the Y's, unbiased, and predictor, okay? Best linear unbiased predictor. So how what is the shape of this blob, which is kind of optimal estimator among the class of linear and unbiased estimators of a linear predictor. Okay, so now for a mean, which is a linear predictor, is a linear indicator. The blob has a very, how to say, simple shape. So you split the sum in the population, okay? The sum in the population, you split it into two sums, sum in the sample and sum in the non-sample, okay? And then the sum in the sample, you have it from the survey, okay? Let's say income, if it is income, it is observed in the survey, okay? But you don't have it for those people that are not in the survey. So that's what you need to predict, okay? So then the blob is obtained by simply predicting the non-sample observations, okay, with the predictions through the model, okay? So it's just fitting it's a mixed model, a linear mixed model. So you just fit the model with whatever function for fitting linear models. There are several packages for that. And with the fitted values, okay, you predict the non-sample values and you replace them there. And that's the best linear unbiased predictor of a domain mean. So it is very simple. And in fact, the beta here is the usual weighted least squares estimator of beta, and the U tilde is the best linear unbiased predictor of U, of the area effect, UD, which is delivered by the functions for fitting linear mixed models. Okay, so very easy, and it has a very nice property, and this property is that you can express the blob in this way. Well, that's when the sampling fraction in the area is small, which is typically the case, because the population size is typically large. What is small is the sample size. So the sampling fraction is typically small, and you can express the blob as a convex linear combination of two estimators. One is what is called the survey regression estimator. Okay, and it is an estimator that is very common in survey sampling. Okay, and it is, look, it is just the sample mean plus some correction using the available covariates. That's the population mean of the covariates, well, the vector of population means of the covariates, and that's the vector of sample means of the covariates. So it's just a correction of the sample mean using auxiliary information. And so that's a very common survey estimator that is somehow, it can be regarded as a direct estimator, because it estimates, you see, one sample mean for each area. So what is important there is that it is using just, you know, it is estimating one parameter for each area. So this makes it inefficient, okay? So you need to borrow strength. So how do you borrow strength? By making this convex linear combination with the regression estimator, okay? That's called the regression synthetic estimator, okay? And here you estimate just one beta, you see, one beta for all the areas. So this beta is estimated with the whole survey data from all the areas where the total sample size is typically really large. So this beta is estimated very efficiently. So this estimator, regression estimator, we have very small variance. It might be biased under the design. It might be biased, but it has a pretty small variance. And the other estimator will be close to be design unbiased, but it will have very large variance. So it is a compromise between the two. And in fact, the weight given, you see, that's the weight given to the survey regression estimator, the survey estimator, you see, this weight depends on the area heterogeneity, which is measured by the variance of the area effects. This is measuring area heterogeneity. So when the areas are very different, or when this variation between the areas is not explained by the available covariates, then it's like the model is poor, and then you give larger weight to the direct estimator, to the survey estimator, the usual estimator, okay? But otherwise, when the model is good, you will be giving more weight to the regression estimator. And also, it depends on the sample size, and the relationship is similar. For large sample size, so if we are estimating in an area with a large sample size, this term will be very small, and the gamma D will approach 1, so all the weight will be given to the usual survey estimator. Whereas, if the sample size is very small, then this term in the denominator will be large, and so the gamma D will be close to 0, and most of the weight will be given to the regression. So, and the regression is using the whole data set, the whole survey data, okay, to estimate in that area. So it will be very efficient. So it is, so when you need it, you know, for the small areas, or when the areas are very different, or perhaps because our model is poor, then when the model is poor, or when the sample size is large, you give all the weight to the regression to the survey regression estimator, okay? To the survey estimator. But when the model is good, or the sample size is small, then you give all the weight to the regression estimator, okay? So it automatically borrows strength when it is actually needed, okay? So that's a good property, and this is thanks to the introduction, to the inclusion of the area effects in the model, okay? If you don't include the area effects in the model, then the estimator will become just the regression synthetic part, okay? Which might be biased. Now, this blob depends on the model parameters, on the true values of the model parameters, which are, they are here, okay, the beta, the sigma u squared and sigma e squared. So you need to estimate them, but using consistent estimators, okay? So as long as you use consistent estimators, when the sample size of the total survey, you know, you are using the total survey, so that when the overall sample size is large, which is typically the case, then these estimators will be close, are expected to be close to the true values. And in that case, you have the optimal predictor, okay? So the eBLAB is not the optimal, but it is close to the optimal when you are using consistent estimators and the sample size, the total sample size is large. Now, what about estimating nonlinear parameters? Okay, so when you want to estimate nonlinear parameters, then a linear predictor on the target variables doesn't make sense. So what you calculate is the predictor that minimizes the mean square error without restricting yourself to linearity, okay? And that best predictor is calculated as follows. You split the area vector, okay, into the sample part and the non-sample part, okay? And you calculate just the expectation of your target indicator with respect to the distribution of the unknowns, the non-sample part, given the observed, given the observations, given the data, okay? So this conditional expectation is the optimal. It minimizes the mean square error under the model, okay? Now, again, it depends on the unknown parameters that you replace by consistent estimators and obtain what is called the empirical best predictor. Well, you need, this predictor requires to know, to have, the set, to have identified, you need to identify the set of sample units and the non-sample units, because you need this conditional distribution, okay? The conditional distribution of the non-sample part given the sample part, okay? So you need to identify which are the sample units and which are the non-sample units. So so you need to, so typically what you have, the data that you have available is the survey data with the sample observations from your target variable, okay? You have them there in the survey, and then you have a census or a register, okay? Census or a register with values of the covariates for each unit in the population. And sometimes the survey units cannot be identified in the census file. Okay, this happens often. In fact, the survey might not have been obtained based on that census. So it might not even be a subset. So there is a, how to say, an extension of this best predictor, of this empirical best predictor that is called census empirical best predictor for that case, for the case when you cannot link the survey and the census. So they are, so the survey is not necessarily a subset of the census. And this is in fact the methodology that is used right now in the World Bank. They did updated their methodology recently this year, and they have now included this method, census EB, and they have how to say, implemented all the software now in Stata, not in R, but they have taken a part of the code from my R package. Okay, so so examples of nonlinear indicators are poverty indicators, and there's a family of poverty indicators called FGT family, okay, that includes several poverty indicators that are of interest. So I describe this family. So you have a welfare measure, let's say income or expenditure for each individual in each area. Z will be the poverty line, and then this family depends on a parameter alpha, non-negative value. So for each alpha, you have a different poverty indicator. And the poverty indicator of order alpha for domain D is nothing but the mean in the area of the product of these two terms. There are two terms. This second term is just an indicator function that is taking value 1 when the person's welfare measure is below the poverty line and 0 otherwise. Oh, sorry, it's very difficult, right? It has gone. And otherwise. Okay, and then this first term, you know, when alpha is 0, which is a particular indicator, when alpha is 0, what you get there is 1. So you end up with the proportion of people whose income or expenditure is below the poverty line, and this is called a risk of poverty rate, or more shortly, poverty rate. And when alpha is 1, note that the term in the sum will appear only when the indicator is 1, that is when E is smaller than Z. So the numerator will be positive. So this is how far I am below the poverty line relative to the poverty line. So this is the distance, relative distance to the poverty line. Okay, so let's say 10%, my income is 10% below the poverty line. Okay, and then you take average for all individuals, for all units in the area, and that's what is called poverty gap. Okay, poverty gap. So the risk of poverty rate is measuring how many poor people there are, and the poverty gap is measuring how poor they are, if they are very much poor or not so much. So how to estimate some of these indicators? So first of all, you need to consider a model. But the problem is that welfare measures, typically when you plot a histogram of the survey data on income or expenditure, you find an extremely right-skewed histogram. So they have a right-skewed distribution, and for a model, it is convenient to have something close to normality. So typically, we transform them, okay, with a one-to-one transformation, and that's a very common transformation. Just to take a shift and log. Okay, that's a common transformation, but it's not the only one. So you can do whatever other transformation from Box-Cox family, Power family, or any other. In my package, you can choose from the Box-Cox family. Okay, and so you write the poverty indicator in terms of the transformed variable, okay, making the inverse transformation of income, okay. You write it in terms of the response variable that will be in the model. And so you have a function of the vector of y's for the domain units, for the units in domain D. And then you just apply the definition of the best predictor, which is just the conditional expectation of the target indicator with respect to the non-sample vector, given the sample part that you can get with the survey data, just taking the transformation of the survey data. Okay. Then you replace the unknown parameters by consistent estimators, and you get the empirical best predictor. This conditional expectation that defines the empirical best predictor can be calculated analytically for certain transformations, okay, and for simple parameters, simple indicators. Now, if you have very complex indicators, or like, I don't know, medians or quantiles, is more difficult analytically. So what you do is to use a Monte Carlo simulation procedure, and that's what is implemented in my package. So the package is for general indicators, okay, because it is using this Monte Carlo approximation of the conditional expectation, and then the mean square error is calculated by Bootstrap. Okay, so let me start with the first application. Okay, so it's an application where we used the basic unit level model that I just described, the nested error model. Okay, but we estimated, in fact, proportions. Okay, so the data that we considered was 2012 data from the structural survey in Switzerland. which is a survey measuring issues related with employment and housing, and 2 administrative registers that were merged in one. Okay, so they gave me just one register. And this register contained a lot of information, very important information that was related with activity, which was the target variable here. So the target variable is to be active, to be in the labor force, or not to be in the labor force. And here there were many variables that were related with that, and they were also in the survey. So you need covariates that are observed in the census or register, and also in the survey, and that are measured in a similar way. Okay, similar way. And they had also information about insurance, social security system. The areas of interest were the communes in Switzerland. Well, I wanted to show you the map of Switzerland. It is here, and yeah, here is the black line indicates the cantons. Okay, and then the borders of the districts are with the gray line. Okay, and the white line is for the communes. White lines. Okay, so there are really many communes. So that's the problem. So you have a survey that is conducted for all the Swiss population, but when you want to disaggregate, for districts and then even more for communes, then the sample sizes become really pretty small. So they might be even ridiculous for some of the communes, or they might be even 0. So that's the small area problem. And here, the target parameter, so there were 2,485 communes in total in the register, but not all of them were observed in the survey. So 10 of them had 0 sample size, and the remaining 2,475 had non-zero sample size in the survey. So we wanted to estimate in the communes with non-zero sample size. I don't like to estimate. It can be done with the model. You can estimate in areas with 0 sample size, but for me, it's too risky because you cannot check the model. Your assumptions should be validated or should be checked with the data. But if you have 0 data there, you cannot check the model. So I don't like to do it. It's like risky because you don't know whether those areas are outlying areas, are different from the other ones. And you have no way of checking that. So we wanted to estimate only in the sampled areas. And we wanted to estimate activity rates, okay, which are the means of the target variable in each domain. And the domains are the communes. The total sample size was really large. Look, 286,000, okay? However, as long as you disaggregate, the sample sizes are decreasing. And look, for communes, there were 356 communes out of the total of communes, which was here. Well, those were the ones with non-zero sample size. Out of them, 356 had a sample size smaller or equal than 10. And there were almost 700 with sample size smaller or equal than 20. So you can imagine, and you want to estimate proportions, in fact, of people in the labor force. So you can imagine that these sample sizes are really pretty small for these target parameters. Now, what about the design? How to include the sampling design in the model? well, in this particular application.
Stop you for a second. Just that you have about 5 minutes left for the presentation.
Okay. Okay, so I will have to hurry up. So in this case, the survey design was Poisson sampling with almost constant inclusion probabilities within certain zones that were defined in Switzerland. These zones, I call them strata. And when we plotted the survey weights, look, the survey box plots of the survey weights for each stratum, okay, for each stratum, look, that's what we found. There are two sets of strata, okay, and in fact, two sets of strata with this practically the same median sampling weight. And there was an explanation of that. The explanation was that they had originally a sampling fraction for each zone, but they allowed some of the zones to increase the sampling fraction. So in fact, there were just two groups of zones. And the variations that we see in the box plots are in fact due to calibration and non-response adjustments of the inclusion probabilities of the survey weights. So they are not actually in the original survey weights, the original sampling weights. So here it was very easy because we just needed to include a dummy indicator of the strata, and we are conditioning on the strata group, two groups, only two groups of strata and just one dummy indicator in the model. And then we included some fixed effects for outlying districts and communes, just one district and one commune that were different. Well, one district was in the border with Luxembourg. Okay, there was explanation for all that. Then we included age groups, gender, civil status, Swiss nationality, owing and secondary residence, household size, income group, contribution to the social security, and some interactions. Okay. And then, well, so the model was fitting pretty well. The failure classification rate was very small, pretty small. So the model was actually very good. These are the usual survey estimates, the GREGs. Okay, the estimates that they were using based on the survey against the EBLABs, And you can see what's happening. So we are estimating proportions of active people. So the usual survey estimates were taking values 0 or 1, 0 or 1 for many communes, which is, it does not make sense, okay? It does not make sense. Whereas the EBLABs were never taking the value 0, and they were somehow smoothing the direct estimators. And this is the reduction in CV that we get. You see, that's estimated CV. And in fact, of the GREGs and of the EBLABs. Those are the EBLABs based on the linear mix model. Okay, and you can see the very strong reduction. That's for a particular canton. For a particular canton, those are the communes in that canton. So here we have the communes. Okay, and it's there. And they are sorted from largest sample size to smaller. And you can see that both estimators, those are the EBLABs, more or less agree, except for the communes with the smallest sample size, for which the EBLABs are smoother. So it makes sense. And this is the reduction in CV, in coefficient of variation, in the same canton. Okay, so you can see we are reducing a lot. In fact, the overall reduction in CV was 90%. Average reduction in CV was. And then I wanted just briefly to describe the application with Palestinian data. Okay, from the using the survey on the expenditure consumption from Palestine and the population census. we estimate poverty rates and gaps. We wanted to estimate in localities, Palestinian localities, from the 319 localities appearing in the census, only 162 were observed in the survey. And so we estimate in those by gender also. And the welfare variable here is expenditure. That's a poverty line in that in their coin, which is the Israeli shekels. And well, we fit separate model for each gender, but the truth is that it was not necessary because the results were pretty similar for the two genders. Those are the covariates that we did consider. Indicators of the two regions, Gaza, West Bank, well, of one of them. Type of locality, rural, urban, or refugee camp. Household characteristics, size, proportion of females, etc. Household head characteristics. Here it is important to say, that the covariates here, include refugee status and other things that are not observed, of course, in other countries. Again, the model fit was really good. All the plots of diagnostics were looking really well for this data. And these are, look, this is the reduction in mean square error that we achieved. Mean square error of direct estimators for all the localities, mean square error for EB. And it is reduced really a lot. We are estimating now poverty rates, and the poverty rates are in percentage. So I multiplied the mean square error by 10,000. So that's the values. The median mean square error for women was reduced from 47 to 6.7. So really very large reduction, and for men also. That's the reduction for each locality in West Bank, and that's for Gaza, women, and well, so that were the estimates, EB estimates. We are using EB method here because poverty indicators are non-linear, and you can see the big difference between poverty rates in Gaza. The median poverty rate was really large compared to the West Bank. And also for the poverty gap, there was a big difference. And again, these are the estimates, EB estimates, and weighted direct estimates, both for West Bank, for women. And look, again, direct estimates were taking value 0, so 0 poverty rate, doesn't make sense. And in fact, the mean square error for those localities will be also 0, the estimated mean square error. So direct estimators are great for large areas, but for small areas are not useful because they might take values that are not nonsense, okay? And then EB estimates were somehow smoothing, were never 0, and the reduction in mean square error was great. In fact, in that application, the reduction of mean square error was about 85% on average. And that's the, I wanted to end with the main message of a small area estimation, which is this one, okay? That union is strength. Okay, so that's all. Sorry for the delay.
Don't worry, thank you very much for the presentation. It was really interesting. There's no applause, obviously, but I think all the participants enjoyed your presentation. I think we still should take a couple of minutes to answer questions. So to all participants, if you have questions, please ask them directly. I have one question myself to start it off. Okay. As a lot of our participants and myself work for an NSI.
Yeah.
And like one of the most common questions we have is when we present survey results, can you give results on, I don't know, in our case, it's the state level, for example, that is always important, which is the smallest is about 200,000 persons only. normally we then have about, I don't know what, 50, maybe something like that, survey units. So the survey area is quite big, but still we don't use small area estimation heavily. There's a few projects. I think Italy is one of the stronger countries in Europe in using that. But apart from that, it's not really used in official statistics. So why do you think the NSIs are kind of afraid of using this kind of methods?
Well, that's a good question. You know, in the States, they started long ago. In the U.S. Census Bureau, they have been using the Fay-Herriot model for a long time. The original paper is from 1979. So yeah, in this sense, I don't know why in Europe we are more too conservative sometimes and don't like to change too much. I think things are changing already. It is, I think, more and more statistical offices are now using small area methods, perhaps not regularly, but it will come. So the only problem of small area estimation is that it's not automatic. That's the problem, I would say. It's not automatic. You need, and when you do something automatic, it is likely not to be correct. Okay, you can be lucky, but it is difficult to do it automatic. So you need to check the model, and the model might change from one year to the next. So you would need statisticians that are there working and checking that everything either is preserved, that the model is the same for the next year, or to find another model. So that's the problem. It's not automatic, I would say. You cannot just program it and leave it there and just apply. You need statisticians to do the work. And
so maybe to follow up on this, how difficult is it actually to find a suitable model, because you probably also have, for the use cases you presented, you had more variables available to use in the model, or was that like the total number of variables? So you probably, if I think about the Austrian scenario or register-based countries, we have a lot of variables for the population that could be possibly used, but the hard work is probably to actually find a good model.
Well, what you need is that the assumptions are more or less satisfied. So that's the basic thing you need. But then, if you don't have many covariates, that's why we include the area effects. So the area effects are protecting because when the covariates are not explaining a large part of the variation of the response variable across the areas, then more weight will be given to the survey estimator. So even if you have just a few auxiliary variables, you can still improve. Okay, so why not to use it? Why not to use it?
Yeah.
You won't do worse. Typically, you don't do worse. And if you do worse, it's just almost the same. It is difficult to do worse unless the model is actually very much wrong. Then of course, you have to check the model. You need to look at residuals. There are many ways of checking. In fact, in the application with Swiss data, we did a lot of simulation studies that I didn't tell here, I didn't mention. Many simulation experiments of different kinds, model-based, design-based, using real data. And it was funny because all of the setups gave similar results. So this indicated to us that the model was good, was actually good.
Yeah. I have a question from Jan Kubacki. Do you think that dividing the set of communes to some subsets, for example, using memberships of commune to cantons, will be beneficial with precision and accuracy of such models?
I don't really understand. So he means to put them together, to group the cantons,
somehow,
make groupings. Yes, that's a good idea. Make groupings of cantons so that they don't have so small sample size. Yeah, why not?
Maybe another good question by him that's also a bit broader. How do you see small area estimations in connection to models that directly use spatial relationships? So not just similarities in terms of auxiliary variables, but actually spatial
correlation. Yeah. Okay, I tell you my experience. You know, I have worked with the spatial models, and my experience is the following. Perhaps people will not like it, what I am saying, but that's what I observed. And I have worked also in other applications, not only on official statistics, but on forestry, for instance. And I got the same ideas than me. Okay, so spatial models are useful when you don't have enough covariates. Because typically the covariates can explain the spatial correlation. So if you have many covariates, typically they explain the spatial correlation themselves. You know, they have the same spatial correlation as your target variable. So then you don't need to include the spatial correlation. It will not, there won't be, you know, the problem is of spatial models is that they are somehow complex. The theory is very complex, so you don't have, and in fact, in small area estimation is much more complex. So you don't have good results supporting the theory, like optimality and so on. It's hard, the theory. So you are somehow in the clouds. We typically extrapolate the theory, but it is not really true. So you don't know what's happening actually. And so if you have good covariates, probably you don't need to include the spatial correlation. But when you don't have good covariates, then you might need spatial correlation. So that's the conclusion.
Okay, thank you. We are already 4 minutes after 11, and we
Sorry.
don't worry, we actually should move on. If you might take a look in the chat or the Q&A and could answer, there are two more questions, or at least one question in the chat I just saw, but I'm afraid we have to move on to the next presentations. But if you can answer there.
Yeah, I will look at the chat. Yes.
So thank you very much again, Isabel, for giving the presentation and also for agreeing to do it virtual, as that is not the same experience as doing it live. Thank you very much.
Okay, thank you.
With this, we are moving on to the first scientific session called Methods for Official Statistics. And the first presenter in this session is Marcello D'Orazio. You should have the right to share your screen already.
Good morning. So I will share my screen.
Perfect. So Marcello, the floor is yours.
Okay, so in the meanwhile, let me thank you, Alexander, Statistics Austria, and all the organizers that make this event possible. So many thanks to all of you for all the efforts done to have this conference this year, in this very strange year. So let's go to my presentation. Basically, my presentation will deal with a very specific topic, that is the distance with mixed type variables. But the reason is that I realized in my last year's working in official statistics that donor-based methods have become really popular in official statistics. We know very well in the imputation of missing values, but also in data fusion or in deterministic record linkage. In addition, so in the past they've been used extensively in hierarchical clustering, but recent with the machine learning and I would say supervised learning methods, we find many donor-based methods for regression or classification. So basically these methods are relatively simple because they require the calculation of distance between observations. The major difficulty is that we have to select the variables and then the distance function. We have many distance functions when the variables are all of the same type, so categorical or quantitative. Few options with mixed type variables. The most popular one is the Goer's distance. This is basically the problem that we face in official statistics, because when we used to take surveys carried out on household, we have a lot of variables that are categorical and some other variables that are continuous, like consumption, income, and so on. So that's the need of having a distance handling the mixed type of variables. The Goer's distance comes from the Goer's similarity coefficient, so it is basically a weighted average of distances calculated variable by variable, in which we can assign a weight to each variable. In the standard version, we assign equal weight to each variable, and I will be back on this, obviously. In the original proposal from Goer, we distinguish 4 different possibility of calculation of the distance. So we have binary variables in which binary symmetric and binary asymmetric. So for binary asymmetric, the absence of the phenomenon is considered, both the unit is considered giving the distance of 1, so not a distance of 0. For categorical nominal variable, we use 1 minus the simple matching coefficient, and if we replace the categorical with the dummies, the distance is 1 minus the dice distance. For continuous variables, so variables measured on an interval or ratio scale, we use basically the Manhattan or city block distance scaled by the range. As you can easily see from this proposal, we do not have something to deal with categorical ordered variables, and so in literature there are some additional proposals from Kaufman and Rousseau or Podani. What is, however, appealing with the distance, with the Goer's distance, is the fact that since each distance for each single variable ranges from 0 to 1, so 0 is the minimum distance, so units that show the same value, and 1 is the maximum distance, it means that the average, the final average, simple average or weighted average, basically will range from 0 to 1. So we have something that has a minimum and a maximum. And the other appealing feature of the Goer's distance is the fact that we can have missing values in the variables. So basically, 2 observations in which one of them shows a missing value do not contribute to the calculation of the distance. If we look at R, I have to say that in R there are many implementations of the Goer's distance. I will mention just some of them. So probably the most known function to calculating the Goer's distance is the AC function in the cluster package. But if we look also at the options for calculating the distance on categorical ordered variables, then it would be better to look at the GoDis function in the package FD. Obviously, we have a specific package that has been developed by Mark van der Loo on calculating the Goer's distance, and this package is very efficient and fast. And then we have the possibility of calculating the Goer's distance and other distance function for mixed type variables in the package Keynote. And more in general, for those that want to have all the various type of distances that can be calculated, I suggest looking at the package Proxy, which implements as well the Goer's distance. So weighting basically, Gowers stresses already in his paper that the decision of a rational set of weight is difficult. So which weight I have to assign to each variable contributing to the distance. The problem, however, that I see is that often this discussion on the weighting is misleading, because the starting thinking is that the variable in the standard version of the Gower distance have an equal contribution to the distance, which unfortunately is not true. And I will provide you a very basic example of unbalanced contribution of the variables. So 3 observations, 2 variables, a categorical variable gender, and then a continuous variable that is age. So if you look at these 2 distances, the distance between the first and the second observation and the distance between the first and the third observation, you see that in practice, what having a different gender determines that units are farther than units that have the same gender but showing a huge distance in terms of age. So basically, if I want to select a donor and I calculate the distance on gender and on age, what comes out using the Gower's distance is that technically I'm favoring units that share the same gender, instead of units, as in the second case, that have a different gender but a distance on age that is really close, 18 versus 28 years. So this is an example of unbalanced contribution. So in calculating the distance, you see that you achieve smaller distances for units that basically show the same value of the categorical variable. This is due to the fact that the distance calculated on categorical variables can only take 2 values, 0 when we have the same value, or 1. On the contrary, the distance on a continuous variable can take the value 0 only when we have the equal value observed, so equal age observed on the 2 units. And the value 1, the maximum distance, is taken only when the absolute distance is equal to the range. And here it comes the second problem. The range, the estimation of the range, is highly affected by the presence of outliers. And so basically, in presence of outliers in the variables, we see that it is quite difficult that this distance achieve the value of 1. So basically, we have to try to improve the calculation of the distance by taking into account these 2 issues. And I have basically 2 proposals, because I realized that the Gower distance is one of the distances that we use mostly when dealing with household survey data. And so the 2 instances are reducing the impact of outliers and balancing the contribution of the variables or having the different nature. So the first problem is relatively simple, because, for instance, instead of scaling by the range, we can decide to scale by the interquartile range. And so the distance should be calculated in this manner. So when the absolute distance between the observation is greater than the interquartile range, we set the distance equal to the maximum. Otherwise, we use this formula here. For the second problem, so balancing the contribution of the different variables on the estimation, one approach that I'm proposing is that of using basically the ideas underlying the kernel density estimation. So this means that basically the distance is equal to 0 when the absolute distance between the 2 observations is smaller than the famous bandwidth in the kernel. Then it is equal to the absolute distance divided by the scaling factor, that can be the interquartile range or the basically the range. And finally, the distance is equal to the maximum when the absolute distance between the observation is greater than the scaling criterion. Here, as a starting proposal, I consider that the bandwidth is estimated using the proposal by Silverman, in which basically we have a constant, the sample size, and the variability related to the distribution of the bandwidth. Another possible modification that goes in the same direction is that based on k nearest neighbor. So basically, if one unit falls in the set of the k nearest neighbor of the reference unit, its distance is set to 0, and so on. In my exercise here, I will consider for the moment just a very basic rule, so k equal to the square root of 1. So to understand if these suggestions work, I've carried out a very basic simulation study in which I have data generated from a multivariate Gaussian distribution. So one target variable that is y, and 5 predictors, 2 of them with a strong correlation with y. Then to mimic the situation, I categorize some of the variables. Then I introduce, in some cases, outlier in x1. And basically, the problem is that of introducing some missing values into y, and then imputing this missing value is using the nearest neighbor donor of deck. And the distance is calculated using the standard or the modified Gowers dissimilarity. So I ran many 1,000 runs for each combination of the starting situation. So the results are summarized basically in this table, in which I have 2 cases, scaling by the range or scaling by the interquartile range, and 4 different combinations of the criteria. So only 1 continuous variable and 4 categoricals, and no outliers on the continuous variables, or outliers on the continuous variables, and the other situation in which 2 continuous variables, 3 categorical variables, but no outliers only on the first variable. And the assessment criteria are basically the first 2 look at the closeness between the imputed values and the true values removed, and the other 2 look at the capability. The first one has been mean, the capability of estimating the mean using the true mean using imputed and observed value, and the last criterion looks at the closeness between the percentiles of the distribution, so estimated using imputed and observed values versus the true percentiles. Basically, I will not go into the details, just look at the summary. The summary says that in presence of outliers on one of the continuous variables, scaling by interquartile range tend to provide better results than scaling by the range, mainly when preserving the true distribution. In general, the modification based on the kernel density estimation with the parameter C106, this is true to the shape of distribution since we are working with Gaussian data, seems to perform slightly better for all the assessment criteria, with the exception of the closeness between imputed and true values. However, I have to say that no one of the proposed modifications seems to outperform the other. So we have a slightly improvement compared to the standard Gowers distance, but no great improvement compared to the problem. So we are trying to slightly improve the problems in the Gowers distance, but we have not great improvement. So basically, however, this first simulation study says that using the standard unweighted Gowers distance is a good starting point, but if we modify it in line with the modification suggested in the paper, we go in the desired direction of improving with respect to the problems. Obviously, further investigation is needed when the quantitative variables, for instance, show a skewed distribution that is very common when observing income or consumption in household survey, and also outside imputation problems, so when I want to perform a clustering or a K-9 classification problem. And finally, obviously, I have to implement this modification in the R, because now I have some very basic function. The idea is that of implementing this modification in the package StatMatch that I've developed for performing statistical matching. And finally, a warning: the major difficulty in applying this donor-based method in official statistics is the fact that we before calculating the distance, we needed to select the variables. Here, I've seen many applications in which the practitioner use all the variables that are available without taking care of the problem. So here, my first suggestion is, first of all, parsimony in selecting the variables. So consider just the variables that are really relevant. Also because even when calculating the distance, in some cases, we have the problem, of course, of dimensionality. So with some distance function, by increasing the number of variables that we use in calculating the distance, everything starts being close to everything. And so we do not have the capacity of discriminating between close and far units. So that's all. Thank you for your attention.
Thank you very much. Very interesting presentation. As we are also developing some KNN imputation methods, that's also of special interest for us. Are there any questions to the presenter? I have not seen any at the moment in the chat. Maybe one other thing is you talked about the weighting and the different variable types. Are you also considering extending the variable types? Because that's something we did for our package, introducing, for example, semi-continuous variables with 0 and some non-zero parts, and they are treated differently. Is that also something you think is important?
Oh yes, you are introducing a very sensitive issue, because I started from the initial proposal from Goer, but you are right, we have many situations in our sample survey in which we have semi-continuous variables, and so you need to take ad hoc modification for end of this specific case.
Okay, thank you. Then just a note from Mark van der Loo that he will probably include this in his Goa package as well, what you've presented. So thank you again, Marcello, for your presentation. And we are moving on to Sylvia Harmening for a presentation on MD, which we also shortly heard in Isabel's presentation mentioned. Sylvia, you have the right to share the screen, so please go ahead.
Okay, yeah, I hope you can see my screen.
Yes, it's
perfect. Yeah, hello from my side. My name is Sylvia Harmening. Also, thank you very much from my side for the organization of this event. Yeah, I'm a PhD student in applied statistics at the Free University in Berlin. My supervisor is Professor Timo Schmid, and I am one of the authors of Package MD. Today, I'd like to give you an introduction of how small area estimation area level models can be estimated by the new package version of Package MD. In general, Package MD is useful for applications in the field of small area estimation and enables the estimation of regionally disaggregated indicators. Version 1.1.7 already contains direct estimation possibilities that are based on survey data and model-based estimation options using the unit-level empirical best predictor approach. But now, in addition, the new package version includes a variety of area-level models, and in particular, the standard area-level model that was developed by Fay and Harriet, and various extensions to account for issues that may come up in real data applications. Here's a short motivation. Imagine the interest lies not on the estimation of the income for the country Austria, but for the 94 Austrian districts. The first map shows the result of a direct estimation procedure that is only based on survey information. And surveys that already exist often are often not planned for the disaggregated levels we are interested in, and show only small sample sizes, which often leads to a low precision of the estimates The precision is measured in terms of mean squared error and is shown on the second map on the slide. And instead of expensive and time-consuming enlargements of the sample size of the surveys, small area estimation methods can be applied. With the help of those methods, the predictions can be improved by using covariate information from census or register data, in addition to the survey data that was used. In the field of small area estimation, unit level and area level models exist, but today the focus will totally lie on the Fair-Harriot model, that is the famous area level model. In short, the standard Fair-Harriot model links area level direct estimators that are based on survey data to covariates that are also aggregated on an area level that stem, for example, from administrative data sources. The CETA het DIR is an unbiased direct estimator for a population indicator of interest, for example, a ratio or a mean. It is assumed to be equal to the population value, CETA, plus a normally distributed sampling error. Even though the model assumes known sampling variances, practical applications, those are usually unknown and they have to be estimated from the unit level sample data. One could also allow for more complex survey designs by considering the sampling weights in the direct estimation, for example, by the usage of a Horvitz-Thompson estimator. In addition to that, the model links the population indicator, CETA, with area-specific covariate information in a linear relation, which leads to the special linear mixed model where the UI are normally distributed random effects, the XI are the covariates, and the beta are the regression coefficients. The empirical best linear unbased predictor is then obtained by replacing the variance of the random effect with an estimate, and the resulting estimator can then be understood like a weighted average of the direct estimator and a regression part. The estimated shrinkage factor is the ratio of the variance of the random effects and the total variance, and it puts more weight on the direct estimator when the sampling error variance is quite small. Therefore, the direct estimator is used when it's reasonable. Lastly, the parameter estimates for the betas, the random effects and its variance are generally obtained by maximum likelihood theory. But the new package version does not only include the standard Fair-Harriot model, but also several extensions are included. The standard variance estimation methods for area level models like the maximum likelihood or the residual maximum likelihood methods are contained, but the standard methods can produce negative variance estimates that are set to 0, although they're supposed to be strictly positive. For those cases, adjusted variance estimation methods are implemented in MD to ensure positive variance estimates of the random effects. When working with right-skewed data, like for example, income or other business data, the assumptions of linearity of the model and normality of both error terms may be violated, and applying a log transformation could be a reasonable solution to meet these model assumptions. The new package version gives the user the opportunity to apply a log transformation on the direct estimator and then to choose between two back transformations. In addition, an arc-Sine transformation can be applied when the direct estimator is a ratio, and therefore the results should take values between 0 and 1. When we give up the assumption of the standard Fair-Harriot model of independent random effects and allowing instead for correlated random effects, and this leads to the spatial Fair-Harriot model, and the MD version 2.0.1 enables the estimation of the spatial Fair-Harriot model that considers a simultaneously autoregressive process of order 1. Then we have a robust area level model for the case of influential outlying observations. MD allows for the estimation of the robust version of the standard and the spatial Fairhariot model. Lastly, when the covariate information stems from larger surveys or alternative data sources, the assumption that the covariates are measured without error can be violated. Therefore, the measurement error model that was proposed by Ibarra and Lohr is also implemented. To evaluate the accuracy of the area level point predictions, the new package version also offers various mean squared error estimators. It totally depends on the model which MSE should be chosen, but we have analytical, bootstrap, and jackknife methods for the MSE estimation. All of the contained area level models can be computed by one function that is called FH. And the version 2.0.1 stays in line with the user-friendly orientation of the version that already exists for the unit level data. Here on the slide, you can see just an exemplary estimation procedure for area level data. For area level models, we implemented even new functions, and here on the slide, they are marked in green. But I will introduce the steps in detail in the following. Suppose we want to estimate the equalized income for the 94 Austrian districts. Therefore, the synthetic example data sets of the package I used. The survey data set contains the direct estimates per area and also its variances. And the population data set contains covariate information that are also aggregated on an area level. The aim of this example is to estimate the income, but of course also to improve the precision of the direct estimates. And we want to evaluate the model and in the end visualize the results. We just start with the first step. The FH function requires one data set that contains the sample and population data. And in case the sample and population data are only available in two different data sets, they can be combined by a merging function that is called combine data. For this short example, we skip the second step of identifying spatial structures and continue with the model selection. The package MD provides AIC, BIC, and the Kullback information criterion and their bootstrap and bias-corrected versions that are especially developed for Fairhariot models by Mawenda and colleagues. The package enables a stepwise variable selection procedure that is based on the chosen information criterion, and it can be compared to the step function that many people know from LM models. In this example, an initial FH object is given to the function and the default setting of the direction backward and the KICB2 information criterion are chosen. Now we can see the output on this slide. It shows the stepwise removal of variables until the lowest value of the chosen information criterion is reached. And then we can also see the function call and an overview of the estimated coefficients of the final recommended model. In this case, the KICB2 is the lowest when only the variables employee cash and cash benefits from self-employment are used as covariates. We arrived at step 4, the estimation of the FH and MSE estimates. We built the standard Fairhariot model exemplarily. In addition to the fixed part, required arguments are characters that indicate the sampling variances and the combined sample and census data set. And in addition, we specified the domains and also activate the MSE estimation. Now we arrived at the assessing of the estimated model, which is also a very important feature when you work with models. This can be done by a summary and by a plot method. We start with a summary method that provides additional information about the data and model components. And here in the output, we can see that the example shows that all of the domains have survey information because the out-of-sample domains are 0. Also, the variance of the random effects are given, for example, and all of the auxiliary variables are significant, even on a small significance value. We can see the p-values here on the right. What we can also see is that the explanatory power is quite large, with an adjusted R-squared of around 0.95. And the results of the Shapiro-Wilk test indicate that normality is not rejected for both error terms. The plot output shows normal QQ plots of the standardized realized residuals and of the random effects. And we can also see plots of the kernel densities of the distribution of both error terms. The user is totally free to modify also the interface of the plots. Here we choose just a simple version of it. And we can see that the output supports the results of the normality test that were also provided in the summary output, except that maybe the distribution of the random effects of this are slightly skewed. You can see it here. If one would not be satisfied with this result, one could apply a log transformation to improve the distribution of the error terms. Yeah, then the Fahrenheit results, FH results, should be consistent with the direct estimates for domains, at least with a small direct variance, or for domains with a large sample size. And in addition, we expect that the precision of the direct estimate improved by using theory information. The comparison can be done graphically by the generic function compare plot. When we use the default settings of the command, the output consists of 2 plots. We can see a scatter plot on the left and a line plot on the right. And except of one high value here, the fitted regression and the identity line of the scatter plot are relatively close. And also the direct estimates are well tracked by the model-based FH estimates here in the line plot. Yeah, then in addition, the input arguments MSE and CV can be set to true, which leads to 2 extra plots. CV stands for the coefficient of variation as a measure of precision. If, for example, CV is set to true, the CV estimates of the direct and also of the model-based FH estimates are compared via box plots, which we can see on the left on the slide, and an ordered scatter plot. And here we can see that the precision of the direct estimates could be improved by the usage of the Fahrenheit model, at least in terms of the coefficient of variation. Then we have the function compare.
I'm afraid you should come to conclusions soon because time's already quite advanced.
Okay, sorry, yeah, I will hurry. Yeah, we have a compare function also. It's like the compare plot function, but it computes a goodness of fit diagnostic. Then we have the map plot function. With the help of the map plot function, it's really easy to visualize the results. What is a nice feature if you want to present your results in the end. And then finally, it's the last step, I promise. You can also export the results to Excel and also to open spreadsheet documents. Here we can see just a short extract how this can look like. Good, then I come to the conclusion. This was just I could just shortly show what the package does, but you could hopefully see that that a variety of area level models is included to allow the user to address issues that arise in practical data applications. All of these methods can be estimated conveniently by using a single function that provides FH and MSE estimates. And a lot of user-friendly tools are provided to enable a whole data analysis procedure. The package version, the new version, is already available on CRAN. And we also added a new package vignette, which includes a lot of detailed information about the package and different examples for the usage of the different area level models. And you can find even more examples in the GitHub repository, MD examples. We are still working on expanding the repository. So if you have any suggestions, ideas, please feel always free to contact us, and we are happy to include even more examples. Yeah, then here I provided the references for the presentation, and I'm at the end. I thank you very much for your attention.
Thank you very much, Silvia, for your presentation. Very interesting. I have one general question. As we are aware, Austria is not the largest country in Europe in terms of population. How is the performance if we would do the same experiment, for example, on German data? Would that be also working on a normal like notebook computer?
Yeah, it would totally work because we work with area level data. We do not have so many observations. It totally depends on the area level that you choose. But if we take districts or even the smaller levels, we have less observations than working with, for example, unit level data, where the computational time is much longer, I guess, than for the area level models.
Okay, thank you. Good to know. I think in terms of times, we move on to the next presentation already, which is given by Giulio. I will just make you presenter, so you should be able to share your screen in a second. Yes, it's working. So,
okay, thank you, Alexander. This is my presentation. Okay, in my presentation dealing with the package sampling strata, new developments and extension to spatial sampling. First, I will give an overview of this package, saying something about recent developments, in particular models and anticipated variants. And I will focus on the extension of its functionalities to cover spatial sampling. In particular methods for optimal stratification and allocation, and also selection of spatial samples. Then finally, a case study based on the particular dataset, that is the MIUSE dataset that is largely used in this kind of experiments. What is the problem? We have a sampling frame. We need to plan a sampling survey in the most efficient way. The optimality can be given by minimizing the sample size required to satisfy given precision constraints on the target estimates, or the dual, in maximizing the precision of target estimates given an overall available affordable sample size. This package can be used to optimize under the first optimality scheme, or directly or indirectly also in the second. How it operates? By considering, given the sampling frame, given all the potential stratification variables in the sampling frame, all the possible stratifications in the frame, and looking for the best one. That is the one that ensures condition 1, minimization of sample size, while satisfying precision constraints. This is done. It is not possible to explore all the possible solutions because it is a huge number. The exploration is is carried out with a genetic algorithm that is very smart in finding a solution, an approximate optimal solution among the in the universe of all possible solutions. There are two possible methods so far. There have been two possible methods for the optimization of the stratification of the sampling frame, and both based on the use of genetic algorithm. The first one we can apply when all the stratification variables are all of the categorical type, or if continuous, we can categorize continuous variables. The second one is applicable when all the certification variables are of the continuous type. For categorical, in the categorical case, the optimization starts from the so-called atomic strata, the ones resulting from cross-classifying units in the frame by their stratification variable values, aggregating atomic strata, and selecting the aggregation that is the optimal one. In the second case, strata are obtained by randomly cutting the interval of acceptable values for each continuous stratification variable and then cross-classifying units. Again, there is an exploration of all these possible solutions until find the optimal one. But it's a bit more complicated than that, because we know that most cases, in all cases, the variables that are available in the frame are not the target variables. So we are not able to determine the real distribution of the target variables in the strata that are produced during the optimization step. We have only proxy variables that are more or less correlated with the target variables. So what we have to do is to try to model the relation between the wise variable, the auxiliary variables available in the frame, and the target variable named z's, in order to correctly estimate the variance in the strata and the overall allocation that will be made, taking into account the real or the predicted variance of the predicted variables in the strata. In this case, we say that we are evaluating the anticipated variance of the solution that we are evaluating in the optimization step. In the current implementation, we have dealt only with continuous variables. The models and the definition and the use are more or less the same that have been implemented for the univariate case in the package stratification. The difference here is that sample strata covers also the multivariate case. We can define whatever number of target variables and auxiliary variables. An important model that can be used in order to correctly evaluate the distribution inside the strata is the linear model with heteroscedasticity. This is of the kind Z equal beta y plus an error component with a normal distribution of the error component. And there is also the heteroscedasticity component gamma. In the case gamma is equal 0, the model is homoscedastic. Otherwise, there is an heteroscedasticity component. Another important development was, in the case of anticipated variance, the possibility of correctly evaluate also the heteroscedasticity component, because we have implemented a new function, compute gamma, in sample strata. So far we are confident that if we use modeling, if we evaluate heteroscedasticity component in the models, we can obtain in a suitable way the anticipated variance, and so the optimality step can be performed correctly. What about another important case, the case in which we have also covariance component. In case Z is the target variable, this is the expression for the variance in the case of this target variable. We can write the variance in each stratum in this way by defining the estimation of the variance in each stratum by defining the differences between the values of the target variable in the units in the stratum. But of course, we have not this available as available these values. We have to estimate these values. We can substitute the term difference, square of the difference, with this more complex expression in which R square is the square correlation coefficient indicating the fitting of the regression model. VEI, VEJ are the model variances of the residuals, and this component is the covariance component. We can take into consideration this component in order to consider also the autocorrelation component that, in case of spatial sampling, can be expressed in this way. In the case that the autocorrelation function is exponential, we can make reference to the ij, that are the distances between couple of points. The distance is the Euclidean distance in the space that can be computed by considering the coordinates, spatial coordinates of the points. And the range. The range is the maximum distance below which spatial autocorrelation can be observed among units, is relevant among units. The value of the range can be determined by an analysis of the spatial diagram. So, given the previous formula for the calculation of variance, instead of including also the spatial component, we have made available in sampling data a third method that is the spatial method for optimization, that consists in supplying for each variable of interest its predicted value for each unit in the frame, together with its associated predicted error, both previously determined by a suitable model handling spatial component. For instance, clicking, but there is no limitation to the use of the different spatial models. So in the spatial model, in order to summarize, any kind of model can be used, parametric or non-parametric. There is no need to indicate the values on model parameters in the optimization step, because we, as said, we give the values of the prediction and also the variance of the prediction. The only parameter explicitly required is the range of spatial correlation. For each unit, so we have to associate in the frame the following information: geographical coordinates, values of predicted values of the z's by means of a spatial model, and values of prediction errors, also computed by analyzing the spatial model. After running the spatial optimization method, and after obtained the best certification, then we can proceed with the selection of the sample. And also in this case, it is important to select the units also taking into account their spatial positioning in order to obtain a spatial balanced sample, in order to obtain the most from the information that we have obtained by considering the positioning of the units. In order to do that, a new function, select the sample spatial, has been developed, which is actually just a wrapper of the function RPM2 KD3 in package sampling big data that is being developed by Lisich and Gresto. In order to give an example of what I've said so far, I just wanted to report this example very quickly. This example is based on the use of this dataset, the news dataset that comes with the library SP. It is a typical example for the application of spatial methods. It is a spatial grid of more than 3,000 points in a portion of the territory near the Meuse River in the Netherlands. In a subset of 155 points, measures have been observed of the concentration of the metals in the soil. So we have a distribution of these metals concentration. We just take into consideration two of these metals, lead and zinc, and the aim is to define a sample survey by which we want to estimate the mean concentration in this territory of lead and zinc. So it is a multivariate simple case of optimization. First of all, we analyze the territorial distribution of lead and zinc concentration, and model this relation with distance from the river by use the Kriging model, we can observe by this variogram that there is a strong spatial correlation until 800 meters. And this is the range that we have to consider when we carry out the spatial method optimization of the sampling frame. So what we are going to do, we do this variogram for lead and another similar variogram with zinc. More or less the distance, the range is the same, slightly different, and the spatial correlation is always strong. So what we do is we fit the two models in this way, and then using these Kriging models, we are able to predict the values of lead and zinc concentration on the totality of the 3,100 points in the Mulhouse territory. This is the input, the fundamental input for the optimization step. We have a frame in which we define as target variable the prediction of lead and the prediction of zinc that we obtained by applying the models. We use these variables also as stratification variables. We submit also the variance for each point estimated by the models. We give the geographical coordinates, and we set as position constraint 1% of maximum expected coefficient of variation on both estimates, concentration of lead and concentration of zinc. Then we run the optimization step. We obtain a total number of final strata, 4 different strata, with a total sample size of 62. This is the form of the strata that have been produced, and this is the territorial characterization of the strata. We can now select the sample, the 62 units from the total overall of 3,000 units that have been selected for the strata, and we can visualize these on the territory of the river. You can see the spatial distribution of the points that is quite even in the territory. This is a result of the new function for spatial selection. Okay, this is an example that has less to do with official statistics, but we can think of the distribution of households in the territory if you wanted to estimate their income. Income is quite has in some situations a high spatial correlation, and if you take into account it, the efficiency of the sample could be very improved. If I had used the linear model instead of a spatial linear model, the sample size here would be 150 instead of 62, with the same precision constraint. So just back to my presentation.
Time's always
okay,
up.
I finished just general information. The paper from which this presentation has been derived is available on the archive. The general information is this link, in particular spatial sampling, is one of the vignettes available in this link. Something about references, that's all. Thank you.
Thank you, Giulio. Maybe one quick question before we move on. Marin asked or congratulates you first on the excellent work. And then he asked if the GA converges to a local minimum in the same way it has for atomic strata. So the genetic algorithm converges to a local minimum.
Okay, I catch the question on the local minimum. Yes, there is the possibility to get stuck in local minimum, and for this reason you have to try different runs of the optimization step, varying the parameters of the optimization step. There are a lot of examples in the vignette that are available for the package. I didn't catch the first question that or just.
It was just one question. I think you answered it. Thank you very much, Giulio. We will move on to the next presenter, Felix Karke, on mQuantRec. You should have the right to share your screen already, so please go ahead.
Yes, thank you very much. Can everybody see my slides?
Yes, it's working.
Okay. First of all, I mean, as everybody, I want to thank especially Mr. Kovarik, but also everybody else who helped in organizing this conference. And I'm very happy to be able to present here. My name is Felix Garke. As my colleague Silvia Harmening, I am a PhD student at Freie Universität Berlin at the chair of Applied Statistics. My supervisor also is Timo Schmid. My package mQuantRec deals with the estimation of linear mQuantile regression and also generalized linear mQuantile regression. Therefore, the title mQuantRec in our package for estimated generalized linear mQuantile regression models. Nicolas Salvati, who is also mentioned here, contributed a lot of R scripts with the estimating functions. So, first of all, general information about the package. It is still under development. So it is still up for change, basically. It has not been uploaded to CRAN or any other website for that matter. It is a regression package, as I mentioned, for the estimation of linear and generalized linear and quantile regression models, which means continuous data can be modeled, binary data can be modeled, and also count data can be modeled, including Poisson, quasi-Poisson, and negative binomial regression models. Also, hypothesis testing via Ward and likelihood ratio tests is applicable, as well as the estimation of Q-scores, which can be used for variable selection and also are very much used in small area methodology. I will come back to the to Q-scores and explain what it is later. Also, the package includes model diagnostics using diagnostic plots. A short excursion into theory from my part. M estimation, step before M quantile regression, is a approach to robust estimation, which was formalized by Huber in 1964. And in this formula here, we can see that we're looking for a location parameter. We want to find a location parameter using a loss function rho. And if this loss function is differentiable and convex, the easier solution is found by using influence functions, psi. And this is also already in the direction of a definition of quantile regression. It's a kind of a robust regression using influence functions. These influence functions are usually the derivation of the loss function with respect to the parameter we are interested in. And then the estimating equations look like this. I have a few examples so everybody can follow along. If we use a squared loss function, for example, we arrive at the sample mean. And if we use the absolute value as the loss function, then we arrive at the sample median. So it is a very general, very broad estimation approach, depending then on the loss function used. Huber proposed a certain kind of influence function, which can be seen here, and it's very important in M-quantile regression. Sorry. I'm very sorry. This influence function relies in magnitude on a tuning constant k, which we can see in this formula. We have two cases. Either our data difference between our data and the parameter of interest and absolute value is smaller than the tuning constant, then we're going with just with the error, basically, the residual. Or if we're looking at a value bigger than or equal to the tuning constant, then we're going with the value of tuning constant times the sign of the difference between the parameter and the data, which means K determines the robustness of the estimator. We are interested in robust estimation. We want to downweigh observations which can be seen as outliers. Therefore, this Huber estimator is very general because it can be seen as equivalent for the mean when K goes to infinity and to the median when K goes to 0. 3. Yeah, this concept was generalized to the regression case by Huber in 1973, and then now begins the M-quantile regression part, further developed by Bracking and Chambers to M-quantile regression for continuous data. And what we can see here, we use the same inference function. We will use the Huber proposal 2 inference function, but now in the context of quantile-like regression, which can be seen here and at the differently weighting the inference functions depending on if the residuals are negative or positive. Here we have the estimating function for the M-quantile regression, where we can see that the estimate MQ hat can be seen as a linear combination of predictor variables or covariates, where xi, of course, are the covariate vector, and beta hat are the estimates of the coefficient estimators. One problem with M-quantiles is that they are not scale equivariant. Therefore, a scale parameter has to be estimated at the same time as the regression coefficients. A few different proposals have been made. First, the mean absolute deviation scale parameter estimator was used, and then later Dorber introduced a corrected version of this estimator. The parameters can be estimated via iteratively reweighted least squares or a newer maximum likelihood approach using the asymmetric least information distribution, which was introduced by Bianchi et al. In 2018. I've been talking only about continuous data so far, but now we get the categorical data. There is a approach to robust generalized linear models by Cantoni and Ronchetti from 2001, which was generalized by Chambers, Salvati, and Tsavides to binary data, by Tsavides, Ranalli, and al. to Poisson data, and Chambers, Deassi, and Salvati to negative binomial data. That's why all of these cases are also included in my regression package, M-quantrack. One last thing before we get into the application of the package. One thing is important for M-quantile regression or M-quantiles in general are the so-called Q-scores. They first were applied by Kokic et al., who used a M-quantile regression model to obtain performance measures of farm productivity. These values can be found by equating the M-quantile value to the real data value and then finding the Q which brings them together the closest in practice. Then we can see that observations with high Q scores also have high values of yi conditional and xi, and that's why they can be seen as some kind of performance measure for observation I. Yeah, these Q scores, why are they important? They can be used in a lot of different ways and are also used in this package. That's why they can also be estimated with this package. They can be used in model diagnostics. They can be used in variable selection, which was proposed by Dorber in 2015. And they are also very useful for small area estimation. For example, when models are employed which make use of pseudo random effects. for example, C. Chambers and Savides 2006. So I have an example where I used EOSILC public use microdata from 2013, and I drew a subsample of 1,000 observations from this data set. As you can see, the input looks very much like one would expect from a normal regression package. We have the formula, and then we also can specify for which Q values, which M quantiles we want to estimate. Here it shows 10%, 50%, and 70%. And the user also has to input this K value, which of course makes the regression a bit arbitrary because the user can switch values as he or she wants. A value of 1.35 is chosen in practice very often just because this gives a 95% efficiency when normal data is used. And then we have the method, which here, of course, is continuous because we're looking at continuous data, but this can be switched for binomial, Poisson, negative binomial, and quasi-Poisson, and so on. I use the scale estimator mean absolute deviation, but also the corrected mean absolute deviation scale parameter estimator is available. And then we see one last option here. I use the likelihood approach I told you about earlier. Iteratively reweighted least squares is also available. For this example, I chose to set the compute Q scores to false. True is the default value. And then, of course, we have a lot of functionality users of regression packages expect nowadays. Of course, we have a print function, which gives the call and the coefficients. And you can see for every quantile we chose in this regression, we get a different set of coefficient estimates. And then the summary, of course, gives a lot more information. Here I chose only to print the summary for the 0.5 quantile. This is repeated for every quantile the user chooses. So we see here an example for Q is equal to 0.5. We see the value of K, and then we get our coefficients estimates as well as the standard errors. There are no test statistics and p-values included yet because there is a void statistic function outside of the estimation of the model itself. Maybe this could be included in the model output directly in the future. And then we have additional information. We can see the proportion of residuals are smaller than 0.5. We're estimating Q is 0.5, so we are expecting something very close to 0.5, which is the case here. And then we can also see, for example, depending on K, of course, how big is the proportion of Bucharest residuals, meaning what is the percentage of observations which are downweight because they exceed a certain amount of loss. And then also we have, as the last thing, we have pseudo R squared, which was introduced by Bianchi et al. 2015, which can be computed for the likelihood-based linear model. And then it gets more interesting. I implemented a variable selection method, which is based on the ideas by Dorber. It is a step function which only functions backward. Forward is not possible, and this relies on the idea of the Q scores. As you can see, the look of it is just as a normal step function one is used to from mass package, for example, or from stats. But the functionality is a little bit different because here's no performance measure is used. Instead, every model has to be estimated in every step. For example, here we have the original model, then this one is the model without sex, and then this is the model without income or self-employment, and so on and so on. And then for all these models, the Q scores are calculated, and then the correlations between the models without a certain variable and the full model are calculated. So we can see, of course, the correlation of the full model with itself is 1. And then we ordered the correlation coefficients from big to small. And then we set a certain threshold. If the correlation falls is above the certain threshold, then the variable is eliminated. Default is 0.95. So we can here, for example, in the first step, because 0.98 correlation is higher than 0.95, sex is eliminated. In the next step, income self-employment correlation is bigger than 0.95, therefore income self-employment is eliminated, and we arrive at the final model. Only including old age benefits and income from employment. Then I have 2 examples for
Felix. I'm afraid the time is running out. Could you move to conclusions soon?
Yeah, sure. I have. I don't need much longer. I have hypothesis testing also included, using either wall tests, which you can see here. We can choose betas, or we can either choose linear hypothesis testing with multiple betas, or we can each test the betas themselves alone. And also we have a likelihood ratio test, which should be an omnibus test, where all the coefficients are restricted to 0 combined. And then I have graphical diagnostics with a lot of different examples. Most of them are also based on ideas by Dauber. I will show just a few examples. I said how important it is because the regression output is depending on the K. For continuous data, there is a way to try to find an optimal K. Here we see the K I chose, which is the one most often chosen. K is 0.345. We're looking to find the minimum of this graph here. Then we have the usual fitted versus residuals. I think everybody knows this. And then we have, for example, fitted versus proportion of negative residuals, and also coefficients over the Q values. So changing Q, I can look at how the coefficients change. It doesn't look very good for extreme quantiles here. And then, another small example with binary data. I will skip this. Now the conclusion. And quantum regression is a field of continued research. Not everything is completely clear yet, but these model methods are very helpful for especially in the context of small area estimation. And I hope that the package and contract I'm writing can be a foundational package which other people can use and go further on with their research. Every user-friendly functions have already been implemented, summary, printing, plotting, and so on, all based on classes. My references, and thank you very much for your attention.
Thank you very much, Felix. I think we should move on right to the next presentation, as it's coming closer to the end of the session, and we have one more presentation to go. So thank you. And coming up is Raphael from Switzerland.
Yeah, I will share my screen. So normally you should see the presentation.
Yeah, it's working.
Okay, perfect. So I'm very happy to present here today at the uRos virtual event. And today I will present a joint work with Professor Yves Tillet from the University of Neuchâtel. That is called spatial spread sampling using weakly associated vector. So it's an algorithm that allows to select a well-spread sample. And the work is already published in the Journal of Agricultural, Biological, and Environmental Statistics this year. So briefly, I will go through a notation, so an introduction to present which notation I will use in the paper and during this presentation. Then I will directly go through the wave method. Wave is standing for weakly associated vector. So behind this method, there is 3 main ideas. So the first one is the idea of distance, the idea of strata, so how we can create strata by using the notion of distances, and then the idea of weakly associated vectors. And so we will define that. And then after that, we have a method that selects a well-spread sample, and then we need to measure how the sample is well spread, and basically here I present two measures, the one based on the Voronoi polygons and the one based on the Moran's correlation. And then I will show some results and a small example on the MERS dataset as well. Okay, so we are in a design-based framework. So we have a population with capital N unit, and then we are trying to select a sample. So it's usually like that. And so here we have a small example. We have 5 units, and we are selecting a sample. So here it's 2, 3, and 5. And we can also write it as a vector of indicator. We suppose also inclusion probabilities, which is the probability that a particular K unit is selected inside of the sample. And for this presentation, I will suppose some spatial coordinates, which are denoted as ZK. And here it's supposed in a general way with a p dimension, but generally we work more with 2 or 3 dimension. And so we suppose also a variable of interest on the population. And so we are trying to estimate here a total, but it could be also a mean or some other quantity. And here we suppose that we use the Horvitz-Thompson estimate. Okay, so the first idea of the method is the notion of distance. So how we can find some good distances. And so the first one that we see generally, it's the classical one, it's the Euclidean distance. So it's the distance between, so it's defined as the difference between the spatial coordinates. So here is the square distance, but for our purpose, it's not really matter if we use the square root or the square distance. And so what is interesting, it could be also interesting to define some new different distance. So for example, if we are working on a grid, which is sometimes the case when we have some spatial coordinates. So here we suppose 9 units placed on a regular grid of size 3 × 3. So here we see the difference unit, and behind the point there is a gradient which show the distance from the first unit to any other point of the grid here. And you see here that with the Euclidean distance we suppose some corners, some edges, and so the distance are less homogeneous than it could be interesting. And so we can also define a Tor distance. So basically the idea is to round the grid to find a donut. And you could see here that it's the same idea. So it's from the first point, and we have a different distances that is defined. And so if we are trying to select some order between the points, then this kind of distance could be interesting if we are working on the grid. And if you have ever played to Pac-Man, it's exactly the same idea. You can pass through the wall to reach the opposite side, or from the bottom to reach the top. So that's the idea of distance, and we can then have some difference distance. Then the second idea is the idea of strata. So how we can create strata by using the notion of distance. And the idea behind that is to use the inclusion probability. So here we suppose a population of 250 units with identical and equal inclusion probability equal to 1/25. So the idea of strata is to, by using the notion of distance, we will find the nearest neighbor of the units until we reach the bound 1. It will represent the neighbor of a particular unit. And so every strata that you could see here, so there are just some example, but every strata, the inclusion probability sum up to 1. And so if you do this not only for particular strata that are in black here, but for the whole population, then you define a stratification matrix. So basically the idea of a stratification matrix is a matrix of size capital N times capital N, where each row of the matrix represents some strata of each unit, and each column of the stratification matrix represents the contribution of a particular unit to the other strata. And so basically the idea of the stratification matrix is giving you the whole configuration by using the constraint that each strata needs to sum up to 1. Okay, so the stratification matrix is sparse and can be highly sparse depending on the inclusion probability. Okay, so now the idea is how we can use this matrix to define a method to select a well-spread sample. And the idea is by using the cube method. So the cube method is developed by Devil in Chile in 2004. And so the idea is to modify recursively the vector of inclusion probability pi, like that. So we start from the inclusion probability, and then we compute the stratification matrix that we just saw previously by using the inclusion probability and the spatial coordinates, so the distance. So how we use the distance to create the strata, that's the idea. And then by using this matrix, we find the weakly associated vector of the stratification matrix. And so the weakly associated vector, we simply, it's simply the vector which is associated to the smallest singular value. So we do a singular value decomposition of this matrix, and we find the vector which is associated to the smallest singular value. And if the rank of this matrix is equal to 0, then we select a vector in the null space, and if it's not, then it's the smallest one. So basically the idea is that we modify the least the configuration. And then we modify the vector by following the direction of this weakly associated vector. And we update the stratification, we update the inclusion probability, and we update the stratification matrix, and so on, until we reach a sample at the end. So we have capital N step to do. So that's the idea of the wave method. And now how we can measure if this the sample at the end is well spread or not. So basically we have two methods, the one based on the Voronoi polygons. So it was developed by Stevens and Olson in 2004. And so it used the idea that, okay, it used that the fact that in expectation, the sum of the inclusion probability inside of the polygon Voronoi is equal to 1. And so the measure is based on the variance of the sample on the fact that the sum of each, the sum of the inclusion probability inside of each polygon Voronoi is equal to 1. And the more, so this measure goes from 0 to infinity, but basically if you are close to 0, then it means that your sample is well spread. And the Morans index, it's a correlation index, so it means that if you are close to -1, then your sample is well spread. If you are near of 0, then it means that you select something randomly, the same as a simple random sampling, for example. And if you have a value IB here that is close to the value 1, then it means that your sample selection procedure is create some cluster. Okay. So here you have just a picture to show you a little bit what is the measure based on the Voronoi polygons. So you see here that we have selecting a sample on a population of 50 units, and the sample size is 20. And so all the inclusion probability here are supposed equal to 0.4. And so we have then each Voronoi polygons that is printed here. And we see that the sum of the inclusion probability inside is more dispersed than the one we used when we used the wave method. Okay, so that's the idea of the Voronoi polygons. And so to just show you an example, so here it's the Meuse data set. So here is the river, and we have some points that are so we have 150 points. And the inclusion probability are proportional to copper level. So you see here that the size of the point is depending on the copper level. So it means we saw directly that we have a spatial correlation for this data set. And so we set the inclusion probability proportional to this copper level. And so you see this example. And so if you are wanting to use the method, then you could load the package wave sampling, which is available on CRAN, and you can download the developed version on GitHub. And so, yeah, the method is simply used. You can load the dataset from the package SP. You specify the spatial coordinates. You specified the inclusion probability. So here we use the function inclusion probabilities from the package sampling, proportional to the copper level. And we specified the size of 30 units. And so then you can simply just launch the function by using the common wave, the inclusion probability, and the PyKey method. There is more option if you are on a grid and you want to use Tor distance and so on, but basically the idea is just easy like that. Okay, and then finally, just to show you some results. So here we have compared to usual method to select some well-spread sample. We have done 10,000 simulation, and we compare to the usual spatial sampling. So here you see the generalized random tessellation, so with GRTS, the local pivotal method, the first method. Here, as CPS, it's for spatially correlated Poisson sampling, developed also by Graf Sturm, and the more recent HIP, so Alton iterative partitioning method. And we compare to the simple random sampling in an equal probability design and the max entropy for the unequal probability design. And so you see here that our method is selecting a more well-spread sample in terms of the IB measure, and as well as for the coronary polygons. So yeah, thank you for your attention. And here you could see some references. If you are more interested in the method, you could check online the paper. And yeah, I will be very happy to answer to your question. Thank you very much.
Thank you, Raphael. Very interesting presentation. It's a bit of a thread of the presentation that it's about spatial information or regional information. Could you give us an idea in what scenarios you would apply that? So probably you would need spatial correlation for it to work or for it to improve the estimation. And if you don't have that, will it worsen the estimation or will it be the same?
Yeah, in fact, if you wanted to select a balanced sampling, you can check that. In fact, if you select a well-spread sample, then it selects a balanced sample. So if you can imagine that you have some also auxiliary variable, and you could define some distances that are, for example, based on the Mala-Anubis distance. This kind of thing could be applied in the method. And so in official statistic, I think you could imagine many datasets that have some spatial coordinates and not so much information about auxiliary variables. And it could be interesting to use a spatial method to select a sample instead of, if you have no really much information about your dataset and you only have your spatial coordinates, it could be interesting.
Okay, thank you. That's good advice. So thank you again, Raphael, and thank you to all presenters in this very interesting session. I think we are just a few minutes after our planned time, so that's also quite okay, I think. Have a nice lunch break, even though it's alone at home probably and not with the whole conference participants. We will see each other again this afternoon at 2 o'clock. We will start the next session, and the WebEx will be open right before, and probably shortly after 1 o'clock I will open the WebEx. So thank you, everybody. Have a nice lunch break. Bye-bye.
Thank you.
Thank you, Alex.
Thank you to all presenters.